Hello everyone, this is Viola, application engineer from Bettersize. Powders can behave very differently at rest and in motion. So today in this video, we will explore why and how different powder characteristics help us understand their behavior from static to dynamic. Powder can create many problems in different industries, uneven dosing in pharmaceutical, inconsistent feeding in food production, breaching and clogging in chemicals, or even production downtime. These problems may look different, but they often share one common factor: powder flowability. So, what exactly do we mean by powder flowability? Flowability describes a powder's ability to flow under gravity and how its behavior changes under different conditions. It is not a single property. To really understand powder behavior, we need to look at it from different perspectives. PowderPro X1 does exactly that, using 18 powder characteristics categorized into 6 key areas to review the full picture. Let's start with one of the most intuitive ways to understand powder flow: angle-based measurements. 3 important parameters are here: angle of repose, angle of fall, and angle of difference. Together, they show us not only how a powder forms a pile, but also how that pile responds when disturbed. The angle of repose is the angle between the freely formed powder pile and the horizontal plane. After vibration, the pile may collapse and rearrange, and the new angle is called the angle of fall. The difference between these two angles is called the angle of difference, showing how the powder responds to disturbance. Another way to look at powder behavior is the angle of spatula. Here, the powder is lifted on the spatula, and the angle is measured before and after a control shock. The average of these two angles gives us the angle of spatula. While this reflects powder-to-powder interactions, we can also look at how the powder interacts with a surface. That brings us to the angle of sliding friction. As the platform gradually tilts, we identify the point where the powder first begins to slide. The corresponding angle reflects the friction between the powder and the contact surface. Next, let's move from pile behavior to how powder is packed and compact. Bulk density describes a powder in its loosely packed state, while after tapping, the particles rearrange and pack more closely, giving us the tap density. But how do we know when a powder is fully tapped? That's where tap equilibrium comes in. By monitoring the volume change during tapping, we can determine when further tapping produces no significant change. With PowderPro X1, the test can automatically stop once the preset criterion is reached. From bulk and tap density, we can calculate these two common flowability indicators. Passability expresses the change as a percentage, while the Hausen ratio expresses as a density ratio. Higher values generally indicate poor flowability. Density can also tell us how much empty space exists within the powder bed, described by the void fraction. A lower value indicates a more closely packed structure, while a higher value means more empty space between particles. Beyond packing behavior, particle size distribution also plays an important role in how powders behave. Here, we look at 3 related characteristics: sieve size, uniformity, and cohesion. Size analysis separates particles by size using a series of sieves. By measuring the mass retained on each sieve, we can determine the particle size distribution. And from this distribution, we can further evaluate uniformity. Uniformity is calculated as the ratio of D60 to D10. It can be used to describe the degree of uniformity in the size distribution of powder particles. Sieve retention can also help evaluate cohesion. Cohesion is a parameter that measures interparticle forces by evaluating the rate at which particles pass through sieves. Typically, higher cohesion indicates poor flowability. Now that we have these individual characteristics, how do we bring them together to evaluate overall powder flowability? This is where Ralph J. Carr Jr. comes in. Based on measurement of around 2,800 powder samples, Carr developed a comprehensive method for evaluating powder flowability. Instead of relying on one parameter, it combines several powder characteristics into an overall flowability evaluation. Each measure parameter is converted into an index score according to the Carr index method. These scores are then combined to give an overall flowability index according to this chart. And this method provides a quantitative evaluation of powder flowability, making it easy to compare different powders or batches. But there is still an important question. Does good static flowability always mean good performance during actual movements? Not necessarily. That's why we also need to look at dynamic behavior, especially flow rate and dispersibility. Flow rate tells us how efficiently a powder actually passes through an outlet. Instead of predicting flow from another property, here we directly measure the discharge behavior. Dispersibility looks at another side of dynamic behavior. That is how easily powder becomes dispersed during movement. This can be especially useful when evaluating dusting and handling risks. Finally, this dynamic characteristic can be combined with the flowability index, angle of fall, and angle of difference to evaluate floodability, the tendency of a powder to become aerated or flushing during handling. The resulting flowability index gives us another perspective on powder handling. So, powder flowability is never just one number. From pile formation and packing to discharge and dispersion, each measurement reveals a different part of the powder's behavior. By bringing this characteristic together, PowderPro X1 helps us understand not just whether a powder flows, but how and why it flows. Thank you guys, and see you in the next video.